Right, everybody, welcome back. Last stretch, okay, last little bit. I know we've done a lot up to now, but I know that you're keeping up and that you're doing really well. So let's see if we can apply it to what I've got in store for you. So I said to you before the break, I'm going to show you what we're doing. We're going to use Lewis diagrams to try and predict the shape. Let's do it. And what we're going to do is I'll show you, but I'll do it with you. And then a little bit later, I'm going to get you to do it on your own. So let's have a look what I've got for you. Determine the shape of the following molecules by drawing Lewis diagrams and using the VSEPR model. So let me see. I've got to use Lewis diagrams and I have to use VSEPR. I think we can do that. Again, you need a periodic table. And let's go. So I'm going to draw boron chloride. I'm going to start with my individual atoms. Boron is in group 3, so that means that there are 3 valence electrons. Chlorine is in group 7, and this time I'm going to use little crosses to represent the valence electrons, and there are 7 valence electrons. Now what I want you to look at is the formula here. It says BCl3. This is going to give us a clue as to what our final shape should look like. So these two together, and this is not a method of how you're doing it, I'm just showing you as we think. So I'm going to have boron. In fact, let me give ourselves some space. Otherwise, I'm going to be drawing over my arrows. We're going to have boron. Then, because there's 3, I think it's going to be trigonal planar. So I'm going to have a little bit of space here. I'm getting too enthusiastic. I'm going to have a chlorine over there. I'm going to have a chlorine over there. And I'm going to have a chlorine over there. And hopefully, if I was to measure it, that would be a 120-degree angle. But what do I need? I need to have my valence electrons for each chlorine. Remember I said to you I'm doing crosses just so that we know who belongs to which atom. Okay, and then my boron, I'm going to use that, that, and that. So that is my BCl3. Now quickly, let's just have a look at what we've got. I have got a bonding pair, a bonding pair, and a bonding pair. So I've got 3 bonding pairs. And do I have any lone pairs on the central atom? No, I've got 0 lone pairs. Does it matter right now that I've got lone pairs on the chlorine? No, it doesn't. Okay, so right now it doesn't matter that I've got lone pairs on the chlorine atoms. I'm just looking at the central atom. Now what about methane? Let's do the same thing again. Carbon, group 4. I'm going to draw it like that. Why am I drawing like that? Because I've had a look at the formula and it says CH4. That means I'm going to use 4 hydrogens. My hydrogen, I'm going to represent it with a little X. And if I put the 2 of them together, and this time I will try and remember to give myself enough space, I'm going to have C as my central one. 1, 2, 3, 4. And then I'm going to have H, 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 and H. And then let me not forget my electrons that belong to hydrogen. So what do I have here? I have got 1, 2, 3, 4. I've got 4 bonding pairs. And I've got 0 lone pairs. Now, I just want to point out something. Remember I said to you sometimes it's difficult to visualize these things in one dimension. If I was to look at the diagram that I've put here, I am definitely not seeing a tetrahedral shape. I don't know about you, but I'm definitely not seeing a tetrahedral shape that I can't even draw properly in 3D. Okay? So that is why making some sort of a model is really a good idea, just to help you get the picture in your head. Okay. Now, as you know with science, when we have a basic idea, we then get more complicated and we add a few things to it. And now we're adding lone pairs. So we had our 5 basic shapes. We had linear, we had trigonal planar, we had trigonal bipyramidal, we had octahedral, and we had tetrahedral. Okay, so we had those 5. Central atoms had no lone pairs. Now our central atoms have got lone pairs. We need to have a look at how that affects the shape. Remember, shape affects behavior. We need to know what the shape is so that we can eventually predict what the behavior of the molecule is going to be. So let's have a look at the board. First one that I've got, here I have got 1 lone pair. Okay, and I have 2 bonding pairs. And it tells us that this is bent. Here, I have got 1 lone pair, and I have got 3 bonding pairs, and it calls this one trigonal pyramidal. And look at this. I've got a second bent molecule. This one has got 2 lone pairs and it's got 2 bonding pairs. Now I can hear some of you saying, well, why does it have the same name? The reason is that shape there, and if we go up, that shape there, they're both the same. Okay, now I want you to just have a look, and I want you to listen to me very carefully. You might look at this bent molecule and think, oh, well, that's just trigonal planar with 1 atom missing. Or you might look at trigonal pyramidal and go, well, that's tetrahedral with 1 missing. Or you might look at the next one and go, well, that's also tetrahedral, but it's 2 missing. Please, 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 please don't think that way, okay? Because the angles are not exact. Right? The angles do change when you have an atom instead of a lone pair, or you have a lone pair in place of an atom. Okay, so don't. Some textbooks do it because it is a nice way to just get the shapes in your head. But unfortunately, it can lead you to a place where you start misunderstanding what's going on because the angles do change and therefore the behavior changes. Okay, so I want you to learn it as when there's a lone pair, this is what it's called. When there's no lone pairs, this is what it's called. I want you to try and keep the 2 ideas very separate in your head. And then when we get onto the behavior, we can start combining the 2 molecules together. I don't want you to fall into the trap of, oh, it's just like this minus one of those. Okay, unfortunately, that can get you really, really confused, and that's not what we want to do at all. So learn them as separate. Your 5 basic shapes where there's no lone pairs, your 3 basic shapes where there are lone pairs. Again, try and keep them separate in your head. Right, so now, what does this mean? It means I'm going to get you to do something. Same instruction. I want you to determine the shape of the following molecules by drawing Lewis diagrams and using the VSEPR model. I keep wanting to say VSEPR molecule, model. There's 3 here. There's ammonia, which is NH3. There's ammonium, which is NH4+, and there is water, H2O. Okay? What I'm going to do is I'm going to go through these with you. If I can find all of them, there we go, apologies. We're going to go through these with you. And we are going to do it slowly. Okay. In fact, I think what I'm going to do is I'm going to do ammonia with you, and then I'm going to get you to do ammonium, and you can do water. Okay, so I'll show you ammonia. So ammonia, nitrogen, element number 5. So I draw my N, and I put my 5 valence electrons around it. Hydrogen, it's group Number 1, did I say nitrogen was element number 5? I mean, it's in group number 5. So there I have 3 bonding pairs. And I have 1 lone pair. Now, what is this one called? This is called a trigonal pyramidal shape. Okay, this is called trigonal pyramidal. Okay, so I've given you the basic when it comes to ammonia. I want you to draw the Lewis diagram and try and guess the shape of ammonium and water. I'm going to give you 2 minutes to do both of them together. 2 minutes starting now. If you haven't finished yet, stop what you're doing. Just have a look at the screen, see where I'm going with it, and see if it's exactly the same place that you would have gone, or if it's not what you would have done, have a look at the right way to do it. So have a look. I'm going to do ammonium. Let's just give ourselves some space here. Move down, and I think I'll extend the page a little bit if I can get our little arrow to work for us. No, it's not working for me. Okay, doesn't matter. We'll make a plan. Okay, so what I've got, ammonium, we'll go with nitrogens. Remember, we draw our central one. 2 electrons, 1, 1, 1. Now, ammonium is NH4+, so that means I've got a hydrogen, and a hydrogen. So where does this other hydrogen come from? The other hydrogen, or the H+ ion, sits at the top, okay? And what it does when it's sitting at the top here, it pretends to share that lone pair of electrons. So it says, look at me, I am sharing a pair of electrons with nitrogen. What's actually happening is that the H+ ion has got no electrons to share. It's got nothing to share. But it just comes and it takes over some of the space of the electrons from nitrogen. And we call that type of bond a dative covalent bond. Okay, it's a dative covalent bond. And hopefully some of you have picked up, we've now got 4 hydrogens. This should be, if you agree with me, and if I can write the word tetrahedral properly, you should be saying, oh, but look, that is a tetrahedral shape. But we said that if there's lone pairs, there shouldn't be a tetrahedral. That's correct. Okay? But because the hydrogen comes and sits here and takes the place or takes up some of the space, we are going to end up with a tetrahedral shape. Now the last one. Let's have a look at water. I like this molecule. I think it's a really cool molecule. Water molecule. I'm going to do oxygen as my central molecule. Now, normally, this is how we would write or draw the Lewis diagram for water. And you're going to have, in one dimension, this nice 90-degree shape. But what we've actually found is that water, I'm going to turn it upside down like this because I think it's got a cool nickname. I'm going to do that, and there's my hydrogen, and that, and there's my hydrogen. Okay, that is the beta, or that is the Lewis diagram for water. Now sometimes you see something called a space or a molecular space shape, or a molecular shape that's in 3 dimensions, or it's a space filling shape, and they will often have water represented like that, and some people call that the Mickey Mouse molecule. Now it's not the official name. The reason they do that is because here is my little hydrogen, okay, there's my other little hydrogen, and then down here I'm going to have my electron pairs, okay, but do you see that there, the space is between them is quite small. But here, the space between the hydrogen and the electrons is quite big. What has happened? This is where the repulsion comes in. These are repelling each other. They are pushing each other away as far as they can without pushing each other off the atom totally. Okay. Guys and girls, we've gone through a lot today. We've done a lot of theory. There are so many more questions that I could ask you, but I'm going to leave it at this point. Well done for keeping up. Well done for keeping track. And I recommend, once again, jelly tots and toothpicks. Go and figure out the shapes, where everything sits in space in 3 dimensions, and use that as our guide and as our starting point for our next session. I'll see you next time. Bye.